So thank you very much for the invitation. I mean, it's always a pleasure to come back here. Two things which have changed since last time. First, I can walk again. So I'm very happy. I'm very pleased about that, and I'm very happy that I have the chance to explore the town a little bit. I mean, which I couldn't do last time. And then, I mean, this is beautiful drawing of Virgin Sinner and Dyer that I got at my last visit. It has been framed and is now hanging off my neck. So yes, thank you. So okay, so the aim of my talk is as follows. So I will briefly explain what an Euler system is. I mean, I had already hinted at that in my last lecture. And I then want to explain how one actually go about constructing something like this. So in today's lecture, I mean, I want to build up a tool set. I mean, generally, I mean, for building kind of potential, well, for constructing Euler system classes, which might or might not belong to an Euler system. And then I want to explain how do we know which of these classes are likely to form an Euler system. Because, I mean, that is not just divine inspiration. I mean, there is actually sort of a conceptual reason, I mean, where one starts looking for Euler systems. Okay, so, I mean, let me first sort of briefly sort of say vaguely what an Euler system is. Euler systems and ETH cohomology. Okay, so I mean, what is an Euler system? Well, we make the following definition. So let V, so let V be a periodic representation. So of the absolute value group of Q. We assume that V is unramified outside a finite set of primes. Outside a finite set of primes. Primes. So, I mean, such representations occur very naturally in number theory. So, I mean, here are some examples. We can take V to be QP with 1. I mean, with 1 means it's the Galois group X, Y as a periodic cyclotomic character. So, this is so actions by CP cyclotomic character. So, or we can take, or we can take V, which is the periodic tape module of the elliptic curve over P. Right. I mean, we will later see. I mean, that there are many other sources. I mean, for such periodic representation. So, what's an Euler system? Well, an Euler system. So, which I will call ES, so is a collection. So of cohomology classes. So indexed by the positive integers. So there's a class Zn lives in the first Galois cohomology, not of the absolute Galois group of Q, but the absolute Galois group of the n cyclotomic field of Q, with values in V, and we assume that these satisfy two conditions. So such that, so firstly, that the classes are bounded, so which means that they take values. So in the GQ invariant lattice, the T inside B. Okay, so then comes the condition, I mean, which gives this name, namely that they satisfy the so-called Euler system norm relations. satisfies the Euler system norm relations. So as n varies. So I mean, the idea is as follows. I mean, you have this collection of classes defined over all these cyclotomic extensions, and you can compare these classes using a sort of homological analog of the Galois norm maps. So for example, I mean, you have this extension, say Q adjoint mu n, and here you have Q adjoint mu nl for some prime L. So this is an extension. I have a class here and a class here, and I can look at the image of the class upstairs under the Galois norm map. And we want these classes to stand in certain relations to each other. So what are these norm relations? I should have given the set of primes a name, so sigma. So the following can happen. So you look at the full restriction map, so from Q adjoint mu n down to Q adjoint mu n. So of the class ZNL, well, two things can happen. So one case is that the class upstairs just gets sent into the class downstairs. Okay, so when does that happen? If L divides N, or if L is an element of sigma union subprime P. Okay. Right, but then, I mean, when L does not divide N and is not in the set, then it's sent to PL of sigma L to the minus 1L Zn. So where sigma L is arithmetic radius. So in PL of X is just the determinant of 1 minus X times sigma L to the minus 1. Acting on the dual representation twisted by 1. Okay. So these here are called the tame norm relations. When you add a new L, I mean, it's a field. So I mean, this gives an Euler system the name because I mean, these here are precisely the polynomials which turn up in the Euler product definition of the L function of the representation. Okay, so in some sense. So in other words, I mean, this infinite collection of classes, I mean, their behavior is governed by these local factors in the Euler product of the L function. So you have to think of an Euler system as a kind of homological incarnation of the L function of this representation. So, okay, so that is an Euler system. So let me make one remark, which will be very important later. We have a theorem, which is due to Soule. So which says that it doesn't really matter for which cyclotomic twist of a representation I construct the Euler system. Okay, so an Euler system for B, Euler system. So for the representation B is in bijection with Euler systems. Euler systems so for the representation V twist K. So for K in Z. In twist K, I just mean a tensor product, I mean with the K power of the representation QT, twist 1. Okay. So this bijection is via an operation which is called Soule twisting. Okay, so I mean, this is not obvious. I mean, Soule twisting is a really sort of really defined construction, but maybe intuitively, I mean, it is clear because I mean, you have these classes, I mean, which are sort of defined over all the cyclotomic extensions. So in some sense, I mean, you can just, if you go high enough, I mean, if you go up high enough in this sort of in the cyclotomic extensions, you can trivialize these twists. Okay, so I mean that makes it intuitively quite plausible. I mean that you can get from an Euler system from B to an Euler system to B twist 1 and so on. So why is this important? So this is important. So because it may be easier, so an Euler system may be easier to construct certain twists. So, I mean, we will see this later. I mean, in some explicit examples, I mean, that for some twists, I mean, one naturally can construct Euler systems, one then gets at the other twists, I mean, via this twisting operation. Okay, so, I mean, why are Euler systems important? Well, here's a theorem, which is generally called the Euler system machine. So, which was first developed by Cato and then generalized by Rubin. So what does this say? It says that if Zn is an Euler system, so and as we know that the bottom class of the Euler system is non-zero, so then we get a bound, so on the Selma group of me. Okay, and then as I explained in my last lecture, once we have found in the Selma group, I mean, we get cases of the Porcato conjecture, Dyer conjecture, and so on. Yeah. So applications. So to Porcato, to Porcato's version and Dyer. And there is another application which I'm not going to talk about in these lectures, but which David and I have just been working out, then the application to the symmetric square of the derivative. Right, well, in any case, I mean, Euler system is a really wonderful thing to have. Okay. So there are two questions. I mean, for the first one is, how does one find an Euler system? They're rather hard to construct. I mean, until a few years ago, there were only 3 known to exist, except the trivial Euler system, where all classes are 0. So that's the one question. The second question is, if you have an Euler system, how do you show this? How do you show that the bottom class is non-zero? Can you give criteria for that? This question is wholly distinct from constructing an Euler system. I mean, as I mentioned in my lecture in December, I mean, we had succeeded in constructing quite a bunch of Euler systems, but we could for 4 years not show that a single one of them was 0. And that was an exceptionally frustrating situation. I mean, we overcame this difficulty, I mean, as I explained then, but I mean, yeah, I mean, this year, so just having an Euler system really isn't it. Well, in any case, so the aim, let me just write down, I mean, the aim of my lectures is we want to study, so to find, I mean, where to look for Euler systems. Where to look for Euler systems and how to construct them. And how to construct them. So what we are not going to do is to give a criterion. So for Z1 to be non-zero. I mean, if you're interested in the latter, I gave a lecture course on that at MSRI, which on the MSRI website. Okay. Right. Okay. So let us first sort of look more conceptually. I mean, for this kind of Galois representation that we want to study. So, a source of Galois representations. Source of Galois representations. So they come from relative ETH cohomology. So we look at X over K. So a variety where K is a number of years. So we can then look at the ETH cohomology groups of X, they change to Q bar with values in QP. Okay, so what can we say about this? Well, this is going to be a finite dimensional QP vector space. Finite dimensional QP vector space with a continuous action of the absolute Galois group of K. So I mean that is quite promising. I mean they are also, I mean, yeah, unless the X is really unreasonable, I mean they'll also be unramified, I mean outside finite infinite primes. Okay. So we will later, okay, so let me just sort of, so later, we will let X and Shimura variety. So we then take I to be the dimension of X. Okay, but for now, I mean, X is just, okay, so this is a good source of Galois representations. And here we already see, I mean, some geometry entering from the underlying variety. And I mean, the idea for constructing classes in the Galois cohomology of such a representation is, I mean, to somehow use the geometry of the underlying variety. So, I mean, for this, so I want to make the following observation. So, maybe for all I, so there is another variant, I mean, of a-type cohomology, and the absolute a-type cohomology. So for I greater or equal to 0 in M and Z, so there also exists absolute a-type cohomology groups. So HI etal of X, I mean, where we do not apply base change, this value is in PM. Okay, so these have no GK action. However, there's a spectral sequence. So these have no GK action. So, but we have the following theorem. Sorry?
Maybe you have to lower this one and then the other one.
Yeah, okay, yes, that works. Thanks. So they have no GK action, but we have the following theorem. So of Janssen. So which says for all X over K, so for all N and Z, so the exists Gaussian spectral sequence. Gaussian spectral sequence. Okay, so what does it say? So the E2 page is given by the HI K of HJ etal. So of X base changed to K bar, this value is into P with N. So, and this converges to HI plus J etal of X, this value is in P with N. So in other words, I mean, we get a relation between the Galois cohomology groups of these periodic representations coming from relative type cohomology. So, and I mean the absolute type cohomology. Right, so what does this tell us? I mean, that tells us that there exist H maps. There exist H maps, so which I will call delta. So where do they go from? So the HI etal, so of X to P plus N. So into the HI etal of X K bar P plus N. And here we want to know it's a fixed part under GK. Right, so we now consider the kernel of these edge maps. So we let F1 of HI etal, that is the kernel of delta. So, and these have a name, we call those the homologically trivial classes. homologically trivial classes. So, and then we get a map. So from the spectral sequence, hello. So then from the spectral sequence, we get a map. So from these homologically trivial classes, hi tau, psi of x, p plus n, into the Galois cohomology group where we want to land, h1k, this values in our periodic representation. Okay. So, right. So suppose now, I mean, we have here a specific representation for which you want to build an Euler system. Well, one approach is to try and construct classes in here and then look at the image, I mean, under this map coming from the spectral sequence. Okay. So the idea, construct classes. So so the question, of course, is why should that be any easier? Well, there is a toolkit, I mean, for doing that, and this toolkit is called motivated cohomology. Motivated cohomology. I never know that I have to write them off in cohomology. Yeah. Okay. Right. So I now want to talk a little bit about motivic cohomology, but in a very sort of hands-on approach. Okay. I mean, I'm going to give some explicit examples. You will see that for certain motivic cohomology groups, I can really write down, I mean, what they are. And I will also explain some operations. I mean, if you have some elements in there, I mean, how you can generate new ones. Right. So what is motivic cohomology? Okay, so here is a really use this definition. It really scared me, I mean, the first time I saw it. Okay, so here we go. So definition. So I mean, let X be a regular scheme. So let X be a regular scheme and I and n be integers. Okay, so then here is extremely helpful definition. So what is this helpful definition? So hi motivic psi of x with coefficients in Q plus n. So what is it? Well, it is a certain graded piece of the gamma filtration of a certain K group. Right. Okay. Yeah, so that's maybe not intuitively clear what that means. Let me just say something here. Here the n matters. Okay. Here the n, I mean, for different n's, I mean, you really get totally different groups. Okay. So I mean, in some sense, I mean, Galois cohomology is fairly trivial that you can sort of go from one to the other. That you can via Solet twisting, but I mean, here n really matters. Okay.
It's H2n minus I guess, right?
Oh yeah, right. Yeah. H2n minus
Because otherwise they will be.
and 9. Yeah, 9 minus 9. Right. Okay, well, before I tell you what this actually is, I mean, in certain examples, I mean, let me just say that Wojewodsky also gave a definition, so a definition of an integral version. So which is related, so two blocks via Chow groups. Okay, right. So what are these speeds? I mean, let's look at some examples, and you will see that it's actually not too bad. Yeah, so I mean, firstly, so if X is connected, so then the H0 motivic, so of X with coefficients in Z with 0 is just the integers. Okay. That's not too bad. So secondly, so if we look at the H1 motivic of X with coefficients in Z plus 1, so this is just the units in the ring of functions on X. Again, I mean, this is not too bad. So, and then, I mean, if we introduce, so if you look at Q coefficients, the H1 motivic, I mean, of X with coefficients in Q plus 1 is just O of X times tensor over Z plus Q. Right, okay, so here's a slightly more complicated example, but still explicit enough. So 3, I mean, this was actually proven in a paper of Landsberg. So in the 90s, so we let S over K be an algebraic surface. So then the H3 motivic. So of S with coefficients in Z with 2. But here is a really nice explicit description of that. So it's given by formal sums say of the following form. So Ni times a pair Zi and Ui. Okay, what are they? So Zi and S is an irreducible curve. So the Ui are in K or Zi star. So in other words, they're just invertible functions on Zi. So when the Ni, I mean, of course, are just integers. So and we assume that the sum of the divisors is equal to 0. So again, this is something to really explicit. Right, that's not the entire truth. I mean, there is some kind of equivalence relation, but I mean, if one wants to construct elements in here, I mean, what we are later going to do is we are going to write down, I mean, so I mean such formal sums with these properties, and then we just look at the image, I mean, under this equivalence relation.
In this condition, some of the divisors, those Ni show up as well.
Yeah. Okay, sorry. Yes, thank you.
I could have added up something with Ni equal to 0.
No. I mean, of course, you're right. Sorry. I mean, later for us, Ni will be 1. Thanks. Okay. So I hope that convinces you. I mean, this definition is not too bad. I mean, at least in certain cases. Well, so motivic formal is useful because there's some very nice factorial properties. Factorial properties. Okay, what are they? Well, firstly, we have cup products. Cup products, we let X be a variety. Then we let I, then M, and N be in Z. So, I mean, then we have a cup product, I mean, from HI motivic, X, Q plus M, so times HJ motivic, so of X, Q plus N, so into HI plus J, motivic of X, so implicit by N plus N. So that is good. And the second factorial property, I mean, that we want is that there exist push forward maps. Because I mean, so the idea is, so if we have push forward maps, we can, for example, take a unit, I mean, something nice and explicit on a small variety, and then push it forward into the motivic cohomology of a big variety, and end up in some much higher cohomological degree. I mean, even if you don't know explicitly what the motivic cohomology group looks like. Okay, so this again, I mean, something we are going to do later. So what are these push forward maps? Push forward maps. So if we have iota, so from Z for X, I mean, is a finite morphism. Finite morphism. So of 4 dimension. C, I know. Okay, now comes the test to see in my opinion. That's true. And I didn't manage to get it all over my dress. Thanks. Right, so what we get some put forward maps. Okay, so we get some push forward maps. What are they? So the push forward map will go from the HI. So more typical, I mean, of Z, I mean, say this coefficients in Z plus N into, so now we have a change of homological degree. So we get I plus 2 times twice the codimension of X is Z and plus C. Okay. Right, okay, so what is the upshot of all this? So we can try, so the upshot is that we can try to build elements, so in an entire in motivic homology group, HI motivic, X, I mean the certain coefficients. So for various I and N, for various I and N, so using a combinatorics, so of units, so push forwards, so products. So, and this is basically for all, this is starting point for all Euler system constructions. Okay, so I mean, we are later going to discuss, I mean, what kind of varieties we want to work with, and in particular, what kind of units we want to work with. Okay, so let me just give some examples. So, here are some examples, and just to explain a bit, I mean, how this might work in practice. So we let Z, so we actually again embed, I mean, a subvariety Z into X, so of codimension C. So this is closed, so close. We will assume that X is smooth. So we can then look at just the trivial class. So in the H0 motivic, so of Z is trivial coefficients. So I mean, you remember this here is just a copy of the integer, so we just take the class, I mean, corresponding to 1. Okay, so I mean, this here, then under, if we look at the push forward, I mean, under the embedding. So where will this live? So this will live in the H2C motivic. So of X is coefficients in Z twist C, and this is called the cycle class of Z. So cycle class of Z. And I mean, already via this fairly trivial construction, I mean, we get some very interesting class. But as I said, one can also start with units. So, for example, if X is a smooth surface, so and we let iota, so in embedding, I mean, of a smooth curve into S. So then we can look at any U in just unit in the ring of functions on Z and look at suppose so this here is the H1 motivic with coefficients in Z twist 1, right? So we can now push it forward under this embedding. So what is this? So this is in the H3 motivic of S with coefficients in Z twist 2. Right.
Very much good question.
Yes.
Is motivic homology the same one that we see clients using the correspondence in this one?
Yeah,
Ah.
you can do that as well. But this here is a description which is used for us.
Okay. Yeah.
Now remember by Landsberg, I mean, this here had this explicit presentation, I mean, in terms of sort of, I mean, sums, I mean, or curves with units on them and so on. So, I mean, this class here has an explicit description, and it just given like the Z and U. Okay. So in this case, the push forward method is really very explicit. And this here is the heart of at least two new Euler system constructions. Okay, where I can say that we will study that in some detail later, where we take Z, I mean, the clear modular curve, and the S to be either the product of two modular curves or Hilbert modular circles. Yeah. So, but we will come back. I mean, at present, I just want to explain how we conceivably might get elements. Yes.
What do you do if these things are proper, then there are no global interesting functions?
Well, I mean, sure. I mean, that is a bit of a problem.
Yes.
I'm not claiming anything, I mean, that you always get something interesting there. I mean, I'll explain later in certain cases that works.
Okay.
But that may well happen. Okay. So right, so we now have a sort of bit of a toolkit, I mean, for constructing elements in motivic homology, at least if your sobriety, I mean, is reasonable, for example. So the question is, how do you get back down, I mean, to Italian homology and then Galois homology? So this is the next section, so which is on the Italian regulator map. Regulator map. Okay, so you know, assume so that X over K is smooth. So and then we let P be a prime, which is not zero, okay. So then there exists an Italian regulator map, so which connects motivic and Italian homology. So Z plus N, so into the HR Italian, so of X with coefficients in ZP twist N. Okay, I mean that again may look a little bit sort of irregular what's going on here, so but here's a remark. Namely, this is a generalization of a very well-known map. So if X is spec K, so I mean then R so from K star into the H1 integral. So okay, this coefficients in that P plus 1 is just a Kummer map. Okay, so right. So now that we have, I mean, well, our tools from motivic homology, this regulator map. NC Hochstellen's spectral sequence. I mean, you can make a vague plan. I mean, of how one may construct classes in Galois homology. So here's a vague strategy. Vague strategy. So for constructing an Euler system. For constructing Euler system. N is psi by 4, let's say for a certain representation, say D is equal to HR eta psi of x bar psi which we then twist by N. Okay, so but it is Z or a direct summand. Right. I mean, I see some of you smiling. I mean, you probably are thinking now of modular curves and C-periodic representations attached to modular forms. And this is precisely, I mean, the example that you should have in mind. And we will come back to that later. Okay, so how do we want to construct? Well, let's not be realistic. Let's not try and construct an Euler system. Let's just try and construct one class, the bottom class of the Euler system. So you just want to construct one element in the first Galois homology of this representation. Okay, so here's the strategy. So we write down a class, write down so a class, so say Z, so in the multiplic HR plus 1, so of X with coefficients in Q twist N using units, pushed forward, so a cut product. So then secondly, we consider the image of this class under the Euler vector. Consider so R etal of Z, so this will then live in the HR R plus 1 etal. So of X is coefficients in P twist N. Then we show that it's homologically trivial. And then I mean we can use the Hochschild spectral sequence to get a class. So in H1Q this coefficient in. Right, I mean of course then you have one class, then the next question is can you build an entire Euler system on top of it? So then the question, so next step, so try and build so an Euler system on top of that. Right, so what I want to do now is to look a little bit, I mean, at the numerology in some examples before we actually come to construct it. But asking, but okay, so first I want to explain a bit the numerology, and once we have done that, I want to address a question. Sure, in principle you have this strategy, but surely, I mean, rather than trial and error, there must be some conceptual way of sort of knowing, I mean, which kind of varieties to look at, which homological degrees to look at, what kind of units or pull forwards and so on to look at. And this is what I want to address in tomorrow's session. Okay. Sorry, but let's.
So in order to get an Euler system on top of the class.
Yes, please, nice. I mean, sorry, because I mean that seems a really strong condition, right? This infinite sort of sequence of classes, I mean, which are related by this weird norm relations. I mean, there clearly needs to be something conceptual going on. Ah, nee, jetzt. Okay. So let us look at some numerology. So when it was 4. So in the first case, we want to look at C over Q in a fine curve. So in this case, so the H2 integral, so of C based into Q bar with 2 P coefficients is equal to 0. So we let V is the H1 integral. So P or a direct solid. Okay. So then the Hochschild-Serre spectral sequence. So the Hochschild-Serre spectral sequence. So this will give us a map. I mean, from the H2 et al. Of C, this coefficients in QT twist 2. Oh, let me see. So QT twist N. So I mean, this gives us a map into the H1 this values in. Okay. Right. So I mean, this immediately tells us, I mean, where we want to construct our classes in a multiplic homology. So we want classes. So the H2 multiplic. So of C with coefficients in Q twist N. So the question now is, well, if I was lecturing to younger students, I'd say you go away and play with it a little bit, and then you come back and tell me for which N, I mean, you can get classes. So, for which N can we construct classes? So for which N can we construct classes? Okay, so for N equal to 0, well, in this case, multiplic homology is 0. So I mean, that's not going to happen. So we have here then the H2 multiplic is equal to 0. So that fails. So if we want to construct something in N equal to 1, so we can look at the cycle class of points. Cycle class of points. I mean, this will lend us, I mean, in the right cohomological degree and in the QP twist 1. Okay. So, I mean, this is actually construction, I mean, which has proved to be very fruitful. So, for example, if C is a modular curve, then we can get in this way, Hegel points. Right, okay, so for N equals 2, okay, how can we get into N equals 2? Any suggestions?
And the couple product.
Yes, excellent, thank you. I mean, we take cup products of units. So of units, I mean, you remember, I mean, that's the H1 motivic QP twist 1. I mean, it's precisely just the group of units. So if you take a cup product, I mean, we land precisely in the right twist. So and again, I mean, for C modular curve, I mean, that was carried out by Carteret, and it's a start of Euler system. So you see, I mean, even this is quite sort of trivial constructions. I mean, you can get to some very advanced, I mean, work, I mean, which has been extremely fruitful in studying the big conjectures. So for N greater or equal to 3, Well, I mean, this can be, so you can see here is y1n. So this can be made to work. Can be made to work. That gives no new information. That gives so no new information. Okay. Can I ask why? Is it easy to explain why? Well, I mean, I guess. Let us discuss that later. Okay. Fine. I don't think it's straightforward, but I mean, they can be short. Okay, so let's look at one other case, I mean, which will be of interest to us later. So in this case B, so when S is an affine surface. Affine surface. So, I mean, here we have the form for dimension reasons, the H3 et al. So of S2 bar, so P is equal to 0, so we let B be equal to the H2 et al. Of S2 bar, QP, a twist n, so or a direct sum n. Okay, so that again, I mean, we can then again play the same game as above. So where do we want classes? So we want classes. So in the H3 motivic, so of S, this value into this n. I mean, again, there isn't going to be a problem. I mean, this class is being homologically trivial or not. I mean, precisely, I mean, for these dimensions. Okay. So, how do we get there? So, well, if n is less than 2, well, then the motivic homology is 0. So, H3 motivic, so of S, this coefficients into this n is 0, so this does not work. So n equal to less than. So yeah. So well, let me first discuss the case n equal to 3, which is the easy one. I'm sure you know that.
I think it's the cup of the cup product.
Quite precisely, and you take the cup product, I mean, of 3 units. So cup product, so of 3 units. So then for n equals 2, well, I mean, here we remember again this beautiful result of Landsberg, I mean, who gave the presentation, I mean, of this motivic homology group. Namely, as these sums of pairs, irreducible curve, I mean, together with units on that. So what we can do is, so if you take a curve, take an irreducible curve, I mean, Z inside S, I mean, via some embedding iota, we let U will be in O of Z, so times tensor Q. So, and then we look at the push forward. So we consider. So the push forward of U1 or iota, so that will be H3 motivic. So of S this coefficients into twist. Okay, so I mean, as I said, I mean, this year has been successfully carried out. So, for example, when S is a product, so of the modular curves, or when S is a modular surface. I mean, of course, and the big question is, what is the unit that we take? I mean, this is a question I come to in a bit. Okay, so for n greater than 3, well, it should be possible, but we have no idea. And people have tried really hard, I mean, to make that case work. Right, I mean, so these are just some examples. I mean, one can go on. I mean, we can now We could look at threefolds, for example, but I mean, I think this is enough, I mean, to give you an idea about it, at least, I mean, to sort of understand, I mean, what is your starting point? What is it you're actually trying to construct? Yeah, so the main question now is, so when can we expect, so that the resulting class, so is part of an Euler system. And what kind of units and subvarieties should we use? What kind of units or subvarieties should we choose? Okay. So the idea. We now sort of say goodbye to general varieties and we concentrate on a very special case, namely Euler variety. So when the underlying variety, so it's a Euler variety. Variety, then we can construct units and subvarieties using automorphic tools. Construct the units and subvarieties. So using automorphic tools. So, and the inspiration, from which units and subvarieties we want, also in this context, comes from integral formulae for values of L functions. Inspiration comes from some integral formulae. Okay. So I mean, we will see, I mean, that there is more than one way in which Euler systems are homological incarnations of values of L functions. Thank you. So let me talk a little bit about the valence and regulator and integral formula. Valence and regulator. So and integral formula. Okay, so I talked about the ETH regulator, so which connects, I mean, motivic homology and type homology. There are also other regulator maps from motivic homology into other homology theories. We have the following fact, which is due to Valenson. So we get, so for x over k smooth, so the k is a number field. So there exists the regulator map X is a regulator. So the valence regulator RB, so this goes from up, smooth dimensions. Okay, so from CH C plus 1 motivic. So of X with coefficients in Q to C. So into the dual of the fill one. So we look at the grade C, the round cohomology of X over C. Okay. So in other words, I mean, we start with motivic cohomology class in here. So then the image under the valence regulator will be a linear functional of this first filtration step of the round cohomology. So let's look at the special case. So for C equal to 2, so in other words, then X is a surface. So we get RB. So this is the map, I mean, from the H3 motivic. So of X with coefficients in this tool. So into the dual of the 1 of the H2 belong of S C. Okay. Right, so the question now is what happens? So suppose that we have an element in here which is given as some like presented by some nice linear combination of irreducible. And there we say units. We look at the image and we evaluate it at an element in the Durand homology. Well, valence improved that there is a very nice explicit formula for that, the theorem. So valence. So Z inside S, so be finite. So the Z is a curve. So we let U be in O of Z times tensor Q. So and we let Z, that curly Z, be the put forward of U along the entering iota. So I mean, as we had seen before, I mean that's an element of the H3 motivic of S with values in Q with 2. Right, so then what is the linear function of S? I mean, psi given by the valence and regulate. So then RB of Z is the following linear functional. So is this a map? So from the fill one of the H2 belong. So of SC into the complex numbers, which is given as follows. If we have a class W there, this is if it goes to the integral. So you take an integral over the C points of that, of the pullback of W integrated against the logarithm of U. Okay. This is a really beautiful formula. So, and let me just make a remark. I mean, here I wrote this down. I mean, when our underlying variety is a surface, but I mean, these kind of formulae exist much more generally. I mean, also for higher dimensional varieties. So, I mean, this here should look somewhat familiar if you had studied modular forms. Yeah, I mean, these kind of integrals, I mean, they sort of, but it looks a little bit like the Rankine set of integral formula, for example. So, but I come back to that in a moment. So let me just write down this remark I made. Remark, so the X is singular formulae, similar formulae, so for higher, so H multiple. Okay, right. So we don't want to specialize. I mean, in this case, so when S is the product of two modular curves. Okay. So but this is of course a Shimura variety. Shimura varieties for DL2 times GL2. Okay. So what does this field 1 of the H2 Duran actually look like? So the field 1 of the H2 Duran, so of SC. So if we have an element in here, so what does this look like? This will look like, so f of minus 4 bar, so d of 4, so d tor wedge, d tor bar for some, so normalized custom eigenforms. Normalized custom eigenforms. So f and g, so which are wave 2 and level n. Okay. So then, we now look at this embedded interest of one modular curve into the product of two modular curves. I mean, just usual diagonal embedding. So we see diagonal embedding. So, and we let u be some unit, so on the modular curve. So now what happens? So we can look, so as I said, we can look at the push forward of this. This will gives us a class in the motivic homology of S. Then we look at the image under the Bayesian regulator and pair it against this differential. Okay, and we see what happens. So what does happen? So if we look at these pairings for RB of so our class Z, so paired against omega, so this will be the integral over one modular curve. So of f of minus 4 bar, b of 4, so log of u, so d tor wedge, d tor bar. And now we really see the similarity to the Rankin-Selberg integral. So note the similarity. So to the Rankin-Selberg integral. Rankin-Selberg integral. So what does this say? So it says if you look at the integral over the C points of a modular curve of f of minus 4 bar, g of tor, so times a certain Eisenstein series. So it begins d tor wedge, d tor bar. Then this is up to an explicit non-zero factor, the derivative of the Rankin-Selberg F function at the point s equals 1. Okay. So, okay. So this is the Rankin-Selberg L function. So, and this here is a nearly holomorphic, so nearly holomorphic specialization. So at s equals 0, at s equals 0 of a family. So of Eisenstein series. Okay. So the question now is, can we find a unit on a modular curve So such that, I mean, this here, we look at the logarithm, I mean, of the absolute value of U, we recover this Eisenstein. So in other words, I mean, are there some units on a modular curve which in some sense are homological incarnations of these GL2 Eisenstein series? Yeah, I mean, if we had that, I mean, then we would be in good shape. I mean, we would construct, I mean, a motivic homology class whose image under the Balian regulator, I mean, would recover the Rankine-Selberg integral formula. So the question now is purely one of the right choice of unit. But I think I'll stop here. I mean,